You will listen in the next, say, 20 or to 30 minutes on an introduction to the Advanced Research Center of Nanolithography. And it is an introduction to the wonderful world of lithography machine, ASML, important company, and ARCNL. And the idea of this talk is to explain what the relationship is between ASML and ARCNL. And for that I can go to our mission. So our mission is to focus on the fundamental physics and chemistry on the world of semiconductor physics and lithography machine. Or in plain language, how ASML challenges ARCNL to help ASML with breakthroughs for the future. And ARCNL is a collaboration between a number of institutes, and it started about 10 years ago. And why did it start? Why would ASML be interested in financing an institute? Well, apparently it started in 2012 with a simple discussion between two people at ASML.
I joined as a former dean of the Amsterdam faculty in the UVA. And then I had a conversation with Martin van der Brink, our chief technology officer, and he complained a bit about individual contributing PhD students. It's okay, but it takes too long, it doesn't make really big impact. And then I said, yeah, that's because you look for individuals and not for a team. And then I started arguing for about 2 minutes. They said, oh, apparently you thought about this. I said, yes, I thought about this. And I think you should hire a full team. Oh, what would that cost? I said, well, first, how long does it take? It takes 10 years. And you need to do it in equilibrium with the academic world, so 50-50. And it takes 10 million per year. So that makes 5 million us, 5 million others, times 10 is 50. He said, please work it out.
This is it. This was the start of ARCNL. The idea that we need academic research, industries need academic research to make progress on the long term, which is called innovation. But to do that efficiently, it might be not asking individual researchers to do things, but to call for a team. And ARCNL is this team. ARCNL is a center where groups work together, meet each other at a coffee machine, and consists of about 100 researchers, about 47 PhD students and 20 postdocs, with 3 departments on materials, source, and metrology. And we are organizationally one of the 10 NWR institutes with a national role in the Netherlands Science, like NICHEF is for high energy physics, we are for public-private partnerships. We are a collaboration where ASML is extremely important for the content, NWI because of the financial and organizational part, and universities for the intellectual contact between our research institute and the academic world. Who am I? I'm Wim van der Zande. I've been director here from 2022 to 2025. And I came here through the University of Amsterdam, AMOLF, our neighboring institute where I have been trained. Then was professor at University of Nijmegen in experimental physics. And then encountered ASML where I worked for 8 years in research and the development and engineering department. And then I returned to here, to my most nice job in the most nice institute that exists, ARCNL. And you see also the name of the present director, Marcelo Ackerman, who came through a similar pathway to the University of Leiden, a number of companies, also ARCNL, and then the University of Twente, to be here director for the next 10 years. So if you visit us, you will meet him. Okay, let's go back to ASML. What is ASML? ASML makes machines that make chips. And chips, everybody knows by now that's very important. If you think about chips, you think about the advancement of iPhones, of the advancement of data centers, etc. And if you look to an iPhone, inside there is a chip. And if you blow that chip up, slowly you get to the smallest structures which you need to make in this chip. And the smallest structures are really amazing. The most advanced chip these days has about 5 trillion transistors on an area of about 20 by 20 square millimeters. And they all have to function in order to operate that chip. 5 trillion transistors. Normally they're a little bit less, but this is the champion number. And in the end, you see structures like this. Structures with lines and connectors, which are made in the machine by having wafers go through the machine a number of times by building up the structure layer by layer. First the transistors, then the connectors, and then the connector outside world. And then a very complicated world of cutting the devices and packaging them and before they enter up in your iPhone. But these typical dimensions, we talk in the tens of nanometer, which is 1/1000th of the thickness of a hair. So on the thickness of a hair, you can place about a few hundred to 1,000 individual operating transistors. That's the dimension you have to think about. This is kind of a cool kind of reference. We are extremely hungry for chips. The reason we hunger for chips is this development here over the years. People discovered computers after the Second World War, and computers were enormous big things where many, many people worked on one computer. When I was a student, that was the situation. I worked with many, many fellow students on one computer, putting in my programs. Luckily, when I did my PhD, the time has arrived when I had my individual desktop on and everybody had his desktop. So the number of sold items with the chip increased and increased. Then, of course, came the time where everybody knows that we all have our instrumentation, our phones, our laptop, our everything, and our cars, which contained an increasing number of chips. But still there were a connection between people and the chips. And now we came into the time where chips talk to chips. If you have autonomous driving, you need cameras and chips to make decisions without any human interference. And that's another explosion in these logarithmic scales of the number of sold units in millions of units. And here is 100,000 times a million units sold per year. And of course, here I added the AI, an unknown explosion of required chips and probably required and generated data. In 2025, the estimate a few years ago was that about 175 zettabyte of data would be generated. Actually, I looked it up. They now think it was 181 zettabyte, but in 2018 we were pretty accurate in this prediction. Now, zettabyte was not in my general vocabulary, so even I had to look that up. And zetta is 10 to the power 21. So 170 zettabyte is 1.7 times 10 to the 23. All physicists and chemists on the people who watch this video will recognize this number as close to the number of Avogadro, 6.0 times 10 to the 23. And for most of us mortal people, the number of Avogadro is the same as near infinity. So this number of data that we talk in the number of Avogadro of things we want to store in transistors and in computers is astronomical. And you like to have a reference, so what does it mean to have this number? Well, think about 1 zettabyte. Here you have a little animal, a fossil animal. It is called the Megaconus mammaliaformis, which means a mammal-looking animal, which was found in a situation where it lived for 200 million years ago. Consider this animal switches on his TV set at birth and never switches it off. 200 million years times 3 times 10 to the 7 seconds in a year times 200 kilobyte is 1.2 zettabyte. So 1 zettabyte is 200 million years of binge watching television. So 170 zettabyte is 175 of those mammals who switched on Netflix 200 million years ago and never stopped it. But of course, we were talking about ASML as a chip making machine factory. And what are those machines and apparatus look like? Here is a machine which works at a certain wavelength in the deep UV, 193 nanometer, and I put the number NA below it, because those are the two characteristics which define the precision with which you can write small structures. The laws of physics tell that the smaller the wavelength, the smaller you can make images on things and details. So that's a natural limit. And actually we make things already of 20 nanometers, 193 nanometer light, which is a mystery in itself. And you have to go to more details to find out why that's possible to do that. And that's not only with light, but also with other processes like resist. It's a complex world. The NA means how many light can you collect? So how big can you make the lenses and mirrors to collect light in order to do it? It's a non-intuitive aspect of physics. If you make the lens bigger, the focus gets smaller. But we get used to it because it comes out of the equations of physics. So 193 is already deep UV, and this can make already structures of tens of nanometer. And in ASML over the years, they have been developing, of course, smaller and smaller wavelength, because that's just their task. So in 1984, they started with mercury lamps at about 436 nanometer. Then it moved up and you see the 248 nanometer pop up. Then the 193 nanometer pop up. And at some point, the thing is, they started with EUV, the workhorse of these days, 13.5 nanometer. The wavelength jumped down by more than a factor of 10, so an incredible increase. But the NA went worse from 1.3 to 0.33. But still the improvement is a factor of 4 or 5. You also see what happens everywhere in physics. If the detail gets smaller, the machine gets bigger. This is almost tabletop, the first in 1984. This is the size of a truck. And the newest generation, this is a group of people standing by one machine, probably of the cost of a few €100 million, which is the high NA 13.5 nanometer machine. And then if you look to the inside, it looks like this. It's an enormous vacuum system. And why it's vacuum? Because 13.5 nanometer light are terrible photons. The photon energy is 90 eV. That means it ionizes every atom it finds on its way. So if it propagates through air, it doesn't propagate more than a few hundred micron or maybe a millimeter, and all EUV will be absorbed. So this whole thing is one of the biggest vacuum ever made, and certainly industrially. And it consists of a source which generates this 30.5 nanometer light. In the previous 193 you saw lenses where the light propagated through lenses. They had to be replaced by mirrors because a lens would absorb all the light. But you know maybe the story of Newton. Newton became famous by changing a telescope from throwing away the lenses and replacing them with mirrors, because he got irritated by the fact that when you look to lenses in those days, because of the chromatic aberrations, every planet was blurred on different colors. And since a mirror doesn't have these chromatic aberrations, he made a big step. And Zeiss is doing the same, so they make a whole set of mirrors. The mirrors propagate light from the source onto the original, which is called the reticle. You see the reticle moving, it's moving fast with meters per second, so that only every time a small fraction of the reticle is imaged by this optical system onto a wafer. This wafer is running around on a wafer table and it's moving to be all the time, chip for chip, being illuminated at the right spot at the right time. How amazing is that? Well, that's pretty amazing, because the accuracy, what is promised to the customer, is in the order of 1 to 2 nanometer, which means that the light, when it leaves the reticle, travels for about 9 to 10 nanoseconds, which means that this wafer, which moves with 1 meter per second, still moves 9 nanometer, which means that by the time the light leaves, the wafer is not right at the right place. So light is not infinitely fast for an ASML machine. In order to know where the wafer is positioned by this robot onto another station where it is measured. Because you can want 1 nanometer, but you have to establish the position of the wafer with respect to the table on this accuracy. So the wafer, markers on the wafer are measured with respect to markers on the side of the table. And even the height profile is measured, because every wafer, which is only 700 micron thick, warps a little bit under the forces of the structure being built on it. And so there's a program made of all the information, and then in feed forward, the table here moves with variable speed in order to make sure that at every point in time the right position is there. And even it moves up and down to keep the wafer in focus. And there are other magic tricks on wafer tables and mechanical engineering, but we are physicists, so we go over the big picture. Okay. So what does ASML ask us to do? Now we said we are a research institute and we decide what we do on our academic program. But you can already understand how many beautiful challenges result from the fact that ASML wants to make a machine with nanometer resolution and precision. And here's a kind of list. So the question they ask us is, can we not increase the number of EUV generated for the source? Or can we make the quality better or the stability better? And this EUV source is already ridiculously strong. I cannot make a comparison, but everybody who would write a proposal to say, I propose a source of 500 watt EUV, would be considered a ridiculous person. But ASML makes it, and we work on it. We have a request to improve the materials. EUV photons are 91 eV, so they attack all materials, and they attack the rest gas into a plasma, which attacks materials. So the request is to have materials which were chosen to be infinitely strong, which turn out to be not infinitely strong in practice, to make them more infinitely strong by doing research. we asked to think about how to put wafers onto a table, making sure that if you accelerate them at 40 times the gravitational acceleration, 40g to 80g, in order to give them the speed of 1 meter per second as quick as possible, that they don't slip, while at the same time that the traction is not so large that when you put the wafer down that it warps because of the irregular contact between the wafer and the different burls on the wafer table. So that's an active study, also that to study the wear, what happens. And a very important one, which is the metrology. You can have the desire to make chips and all these structures, but how do you know you make what you wanted to make? And since the value of a lot of wafers grows into the millions of euros during the process, you want to be in time to say, I have to throw these away because something went wrong. And that's the art of metrology, that layer by layer you check, do I make what I wanted to make, and is the quality good enough? And since the structures are way below a wavelength, we also need metrology tools. So the same challenge which we have in writing it is the same challenge in seeing it. Because to see it, we need to use light or other means, and the natural wavelength of the light is much longer than the structures. So metrology needs, how can we beat physical laws and do deductions on the structures which has been made in the machine in order to make the decision it's okay or not okay. And there we all have big dreams to not only look at the structures, but maybe even look at the functionality on the scale of the individual structures on the devices. And the last one is that the biggest enemy in the lithography machine is the particle contamination. A single particle in a reticle will be imaged on all the chips, and you can throw away the lot. And the machines are so clean that you talk about single particles per 1,000 or 10,000 wafer passes, so that it went through the machine and back, but every 10,000 times you see. So there is a challenge in, can we see particles? Can we understand their mobility within the machine under influence of the light and other things? And in some sense, can we prevent particles? Some particles coming from the source and consisting out of tin. Okay, well, this is the aspect of the ASML perspective in what they ask us to do. Of course, there's one important question which is left over, because ARCNL has an Advanced Research Center of Nanolithography has a natural acronym, ARCNL. But some people...
ARCNL or ARCNL?
I think it's ARCNL.
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 ARCNL. It's ARCNL.
ARCNL for sure.
I think it's ARCNL.
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 For me it's ARCNL.
It's ARCNL.
Okay, for everybody who's listening and will visit ARCNL or ARCNL, don't worry about making a mistake in the name, because we don't have a fixed definition and we leave it open to the preferences of the people. So let's go a little bit to the ASML perspective. What are we doing? I cannot tell everything. For that you have to go to the website and inform yourself or just visit us. But let's go to this magic source of making this EUV. This is a movie still generated by ASML about the principle. We use tin droplets. Well, let's go one step back. There was a laser once of 193 nanometer. That was the lowest frequency you can almost make with a laser which is stable. 13.5 nanometer breaks everything, so that means you cannot make a medium to create a laser. So you have to go back to the old light bulb physics. You have to heat up things to the temperature so that they naturally start to emit 13.5. The temperature where that happens is around 500,000 degrees. So the only challenge is make something which you can heat up to 500,000 degrees. Which means you need to be lots of power, and you do that by taking a short pulse and in a short time heat up a particle to this temperature, which are tin droplets. The tin droplets have about 10 to the 14th atoms, and for the physics and chemists listening, there's about 10,000 electrovolt available per atom. So you can ablate, ionize once, twice, 3 times, 5 times, 10 times, 14 times, and still pump in energy in this plasma, which then is converted to EUV radiation. Since it's a light bulb, it goes everywhere, and it is collected by a mirror and then focused. And the real-time power when the droplets start emitting is in the order of megawatts. Somehow we're used to these commercial numbers of a few hundred watt. With effect, we do the physics of an EUV source which has a megawatt real-time power during the emission of a droplet. Okay, so how do we study that? Well, we are modest. In ASML we use 50,000 droplets per second, here we use 10. But the compensation is that we can have way more subtle diagnostics. All those tubes you see behind me are different diagnostics. One type of diagnostics is a so-called shadowgraphy. Shadowgraphy is you can shoot another short laser, and whatever matter it meets, it creates a shadow onto a camera. And by that you can study the effect of a pulse which deforms the droplet first into a pizza or pancake, and then of the laser which blasts the liquid into this plasma matter in order to start to emit the radiation. And let's go to a picture what you can see when you do such an experiment. Here you see a droplet which is expanded into this elongated slab. You see all these droplets. And this is done by droplet, taking an image of a shadowgraphy. You also see that after a while, and that while is about after 3 microns, you see something, a black cloud. The question is actually, what do we look at? Everybody understands that if you have a pure liquid, that the shadow will be a real shadow. Consider you have atoms or many small particles, when it will be black, when it will still be transparent. So there has been a study to study those effects, and those study effects is that there is an observed pulse, that is every time the pulse after a certain time which creates the blackness. There was a pulse to create this pancake, and there is a pulse to evaporate this pancake and see what matter do you create if you do that. In order to see that, you can have 1 degree of freedom, which we can introduce. That is the wavelength of this laser which looks at it. You can take a wavelength for shadowgraphy which is sensitive to individual atoms. If you have many atoms, it becomes black. But you can also take a wavelength which is insensitive to atoms, so you only need liquids to make it black. So we can different pictures of the same physics at different wavelengths in order to deduce what's really happening. And that's what has been done by the group of Versolato, by a whole team of people. And here you see the wavelength chosen to do the shadowgraphy. And at every wavelength, they took those pictures. So this is a picture where you see the change after a certain set of times if you scan the wavelength over the whole curve. So you see that the same physics gives complete different pictures whether you're this wavelength or this wavelength or this wavelength. They also see these lines, and these lines are characteristics for the fact that matter consists also of atoms, which are as individual atoms have sharp absorption lines. So if you scan over this one, then you see this number changes very little, just these points, and you see that the blackness of the background changes a lot. If you combine all these data, you learn that what matter is. The matter you have is partly atoms, partly small particles, and that's important information to optimize the efficiency of a source like this. The second challenge we have is in our metrology department. Metrology is seeing what you cannot see because it's not allowed by law. So how do we do that? We have to, this is an electron microscopy picture. This is a reality of a future device which has so many layers. You have to learn to look, how do you check whether the quality of all these layers are still properly on top of each other? And one direction is that you think you have to make an image. You can also make an image, the information of an image, by taking a light beam which you scatter onto an object, and you just looked at the scattered light. You get an image which you cannot interpret unless, but it is deterministic. It's determined by the structure. Every structure gives a different image. So now the task is, can you invert the kind of random looking diffractive information onto an image onto what the real structure was? Physics tells that it is not possible very easily because a camera only measures intensity of light, and since it's diffraction, it's really the wave nature, so you have to find the wavefront. But people are smart and they can find ways to deduce what the wavefront looked like, which gave this intensity pattern, and that combination of information can be deduced to what the structure is. This is an example of a sample which looked like this. This is the scattered pattern onto a camera, which after taking enough data and information was deduced to this real-time structure. So this is what is called lensless imaging. And the advantage of lensless imaging that you can use wavelengths for which you don't have lenses, like very short wavelengths, and can still do metrology. And that's done in a number of groups here. Another way is if you have to go to samples where light does not penetrate. There's a group who realized that you can also use sound wave. You can use a very short laser pulse to get a shock wave on a certain position, which then propagates as a sound wave to the matter, feels everything which is below, scatters back, and then have another pulse to look at the deformation on the surface because of the returning sound wave. And the fun part is, with sound you always think about long wavelengths, with hypersound in matters has a natural wavelength of 100 nanometer. So we're back in this realm of where we like to be, the nanometer scale to deduce information. A last one is to go for shorter wavelengths. And to show that we're an academic lab, we're close to a Nobel Prize of 2023. The Nobel Prize was, among others, earned by An Luyé, who many years ago, in 1988, took an intense laser and shot it into a gas, just as academic curiosity. The laser was 1 micron, and she looked to a spectrometer and she found all these discrete peaks. So nature transformed long wavelength light in short wavelength light just by using its intensity. And that came the Nobel Prize. The underlying physics is that if your laser pulse is strong enough, it can pull out an electron from an atom. It turns around by the electric field, it recollides, and the energy it has gained by the electric field of the light can be used to make the photon of a shorter wavelength. Okay. At ARCNL, and also at other places, we realized that you also can make this process of short wavelength generation by having an intense field, not only on a gas, but also on a solid. Which was in the beginning a little mind-boggling, because didn't we say that you need to pull an electron away, which moves, goes back and turns, which in a vacuum is easy to envision. But in a solid, then this electron moves by 1 atom or 2 or 3, and why is it not deformed? But it works. And actually the fact that this electron has to keep its place turned out that this process is sensitive to what you do with the rest of the atoms. So if you take a second laser pulse and shoot it on the same solid which makes this harmonics, you can confuse the electrons in not returning back on a coherent way and create light, but they forget where they came from and they cannot make UHV anymore. They cannot get these harmonics. And that was used in a group of Peter Krauss. So here's the excitation with a long wavelength. You get this harmonics, which is shorter wavelength, which already reduces the accuracy of where you can pinpoint it. Then you take an extra laser beam, which you make in a donut, so that on the outside you confuse the electrons, and there's no longer high harmonic or short wavelength radiation generation, and the peak gets smaller. And this is what we always want. The narrower the peak, the better the resolution. And that's why it's called embaptized super resolution spectroscopy, and it has even the acronym of HADES. Does it work? Well, this is the spot behind the solid which you illuminate with an intense laser field, and then you get this third or fifth harmonic being generated. Here's a donut beam which they generate, and then what happens when they put it on top, you see the high harmonic shrink. So this is the first step onto a long path of reducing this from the many microns of the first pulse to the tens of nanometers in the future and realize super resolution. And if you want to see it as really an experimentalist, I'm sure had a great day when he or she switched on his laser on and off and saw the spot on his camera accordingly shrink and increase. Okay, with these examples, which are only a few, of a much broader scope of groups inspired by the challenges of ASML, I hope I give you a flavor and arouse your interest in ARCNL and its research program. You can go to the website or consider a visit to the Institute. Thank you very much for your attention.